Okay, so we're going to talk a little bit about the first law of thermodynamics, which you've heard before. Energy is conserved. So whenever heat is added to a system and energy, it transforms to an equal amount of some other type of energy. So energy is not created or destroyed in the universe. For thermodynamics, what we really have to do is define our system and the surroundings. And we've done this before with momentum and collisions and that kind of thing too. So we're really going to talk about what is our system, and that's going to be the part that we're studying. Quite often it will be a sample of gas. So if you're in chemistry right now doing gas laws, this will kind of come into that a little bit too. That will be our sample of gas, generally air. It doesn't have to be, but often it is. And then surroundings are everything else in the universe, literally everything else. Okay, so for a couple of things we're going to be looking at, we're going to look at heat flow. And when you think about heat flow Q, this is heat in or out of the system. Heat in or out of the system. And we're going to talk about work that's being done. And think with work, think about a volume change. So if there is no volume change, there is no work that's done. And we'll talk about that in more detail. And internal energy, think temperature change. So U is not temperature, but think about temperature change when we talk about U, our internal energy of our system. So let me give you some examples here. Let's say that we put an airtight can on a hot plate of some sort and turn it up to 10. Well, not a great idea because what's going to happen here is this is going to start to boil and expand, and eventually, not such good things are going to happen. Kaboom. The can has a fixed size, no volume change, so no work is done. So what's going to happen is all of that energy is going to go into increasing the internal energy of the enclosed air here. So our internal energy change is going to be positive. I should say change in internal energy. So no work is done because this is an airtight can. There's nothing that the air molecules can do. But what if we, instead of putting an airtight can, which is a bad idea, we put a sort of movable piston. And this movable piston could go up and down as we heated this up on our little hot plate here. Heat it up, and the gas starts to form, hits the sides of the container, the pressure goes up, and the piston would go up. So what would happen here, some of the heat, some of this internal energy would go into doing work, pushing the piston up, and then the internal energy would not be as great. So work would be positive because system is doing the work. We'll look at a little chart of that, but work is positive because the system, which is going to be our water, our air here, is pushing this upward, and when that happens, work is going to be positive. All right, so the other thing to talk about here is that we can change the internal energy of a system without adding heat. I can increase the internal energy or decrease the internal energy without adding heat. If we do work on the system, for example, compressing it, so I'm pushing that piston down, the temperature will rise without an input of heat. Now, again, because we have three things we're kind of juggling here, heat could be added or removed if delta Q is heat flow, positive if heat flows into the system, negative if it flows out, to maintain a temperature if we're interested in maintaining a temperature. But if we don't do that, if we don't add or add or remove heat and to maintain a temperature, the temperature is going to rise in this situation by compressing it, or it will drop if I expand it. Again, if work is done on the system, it is negative. If work is done by the system, so I always think piston up, and this one piston down. Okay, so like I mentioned in the last slide, if a system expands, expanding against its surroundings, piston goes up, then the internal energy will decrease. Now again, heat could be added or removed to change this, but without that, the temperature will go down. Work is done by the system, so it is positive. again, if no volume changes, if we don't have a movable piston, then work is 0. And we're going to look at a couple of these things in just a second. Okay, so let's talk a little bit more about Q. The process of compression or expansion of the gas so that no heat enters or leaves the system. So again, I have a choice if I'm going to have heat entering or leaving a system. Or I can try for something called an adiabatic system. So whenever I go to Caribou and get some coffee, what we're trying for there is an adiabatic system, a system where heat is not allowed to flow in or out of the system. And of course, when you have hot coffee, you don't want it to flow out. You want it to stay as hot as possible for as long as possible. And I suppose a thermos, if you have some cold drink, you don't want the heat to come in. So you're trying for this adiabatic process. Now, a couple of things you can do. Like I said, you could insulate the system, really good insulation, so you don't allow that heat to flow in or out. Some materials are better for that, and less than that. Or, and this is what diesel engines do, you can compress or expand really, really fast so that heat doesn't have a chance to come in or out to any appreciable amount. And so if you can do it really fast with a diesel engine, it's 1/100 of a second, then you can reach a temperature so high that it can ignite a fuel mixture without a spark. So diesel engines don't have spark plugs. All right, so to summarize here, if work is done on a gas by compressing it adiabatically without heat entering or leaving, the gas is going to heat up. Now Q will be 0. Work is going to be negative because we're compressing it, pistons going down. The internal energy is going to increase positive. If work is done by the gas, by the system, by expanding it, think piston going up, again, adiabatically, Q is 0, the gas is going to cool down. Work is positive, internal energy, U, will decrease. The change will be negative. All right, so a couple of things to look at here. Again, if the volume doesn't change, no work is done if that piston isn't moving. But if there is a volume change, let's just think about this. So right now, take a second to pause, blow air from your mouth onto your hand with your mouth forming a large O, like you're trying to warm up your hands on a cold day. The air is warm because you're warm, 98.6. Now, blow air through puckered lips. So take it and you've gotten a burn on your finger and you're trying to cool it off. You're going to pucker your lips and you're going to blow and the air feels cool. Well, why is that? Well, what's happening here is a blob, and that's actually a technical term, which is kind of funny. A blob of air is being compressed with your lips and then it's expanding outward. So what you're doing as it's going through your lips, I can't draw lips, but you're compressing it and then you're letting that blob of air expand. And when it expands, that internal energy is going to drop. And you do it fast enough so it's pretty adiabatic. And it's going to expand and it's going to cool. Chinook, the wind that blows down from the Rocky Mountains across the Great Plains, is warm because cold air is moving quickly down the slopes of the mountain. It's compressed, and when that's compressed, it's warmed up, and that's a nice end to the winter. Airplanes actually have to use air conditioners. If you've ever been on a plane before takeoff, I don't know exactly what they do, but it's hot in there, especially on a summer day sitting on the tarmac. It's really warm. Now, they actually have to extract heat from the cabins even at a high altitude, even when outside is negative 35 degrees Celsius. And why is that? If we're so cold outside, why in the world are we using air conditioners in the plane? Because the cabin must be pressurized. Okay, there's not enough oxygen up there for us. And so they take the air in, they compress it to have more oxygen molecules per square meter or cubic meter, and we have enough oxygen to breathe in the cabin. But the consequence of that is there's a huge increase in temperature. It would be unbearably hot inside of an airplane if the air conditioners were to stop working. Okay, so one of our big formulas here is going to be internal energy change of a system, the change in internal energy. And this makes sense because it's heat that flows in or out and work that's done. So we take consideration of, okay, how is that internal energy or temperature going to change? well, what are we doing heat-wise? Heat flowing in, heat flowing out, okay. Minus what we did as far as work goes. So let's take a look at a couple of these. Again, a synopsis here where U in the internal is the internal energy of the system. If there's a temperature increase, it's positive. Decrease, it's negative. Isothermal, keep that term in mind. Iso meaning the same, thermal, the process of delta U is 0. Q is heat added or removed from the system. If the system gains heat, it is positive. If it loses heat, it is negative. If you see the word adiabatic, Q is 0. Now, you can calculate this from our past formulas of Q is equal to heat capacity times mass times change in temperature. Or if you're changing state, you can just take the heat of fusion or vaporization times the kilograms and you get joules. Oh, by the way, these are all joules, right? That's energy or heat. Work is W is the work done by or to the system. And again, I've gone through that. If there is no change in volume, isovolumetric or isochoric are the terminologies there, W would be 0. So a couple of examples that we'll look at here. What if I had, and let's just keep this pretty simple, let's have a system here and the surroundings here, and this could be, again, those, that piston, that cannon piston on the stove, and surroundings here. So what's going to happen is, in this one, I've got 1,500 joules of heat gained by the system. So we're going to have 1,500 joules of energy going in. The work is done by the system on the surroundings of 2,200 joules, and that's going to be our work. Now, when the system does that to the surroundings, this is a positive. Okay, and when heat flows into the system, that is also positive. So we have to make sure what our numbers are. We have to understand what's happening and realize that those are both positive numbers. And then when I say, okay, how's that change in internal energy going to go? Let's say Q minus W. I'm going to have, 1,500 joules of energy flowing in, but I did 2,200 joules of work. And so what we end up with is a negative 700 joules. The internal energy is going to drop. Our temperature is going to drop here. And that makes sense because it's almost like you took in $1,500, but you spent $2,200. So your bank account is down $700. Kind of makes sense. Let's look at this one. 1,500 joules of heat is gained. Okay, so we still are going to have 1,500 joules, and that'll be our Q, and that's positive. And then 2,200 joules of work is done on the system by the surroundings. Okay. All right, so now what we have is a negative amount, and that's our, oh wow, and that's our W. Okay, so this is like you took in $1,500 and you took in $2,200. But when work is done on the system by the surroundings, our W is negative. So what happens here with our internal energy? Well, our Q minus our W, what ends up happening is I've got 1,500 joules minus a negative 2,200 joules. So the signage is going to be really important there. I am up 3,700 joules. Now, if this were dollars in a bank account, that'd be awesome. However, this is actually not great. This would be like if we had a piston, and the piston is pushing down, and I'm also heating it up. The air in there, that system, is under, is getting heat, and heat's flowing into it. Also, it's being compressed. We're talking about a fairly high change in internal energy and temperature there.